Okay, in this video I'm going to be working through some of the examples from the mixed integration practice worksheet that I posted on my Canvas page. And so this might be a good companion video while you're working on the worksheet, or if you've already done it, to come and check yourself so you don't wreck yourself. So here's number 3. I'm not necessarily going to do all of them, but I'm going to work through a few of them. This is number 3. Is the classic integration by parts type problem, because I've got a power times an e to the, and we know the e2 doesn't change much when you integrate it or derive it, so it's great. It works nicely with integration by parts, and of course x squared gets nicer as you derive it, so it works good with integration by parts. So in this case I'm going to let u equal x squared, which means du is equal to 2x dx. Then I'll let dv equal e to the 6x dx, which means v is equal to 1/6 e to the 6x. So then, of course, I'm plugging into that formula uv minus the integral of v du, and so my uv is going to be 1/6 x squared times e to the 6x minus the integral of v du, and that would be, let's see, 2 times 1/6 is 1/3, so that'd be 1/3 x times e to the 6x dx. But then we see that we need to do another integration by parts, because we've got it down from an x squared to an x, so we just need to do one more. So I'll once again let u equal, this time I'll let it equal 1/3 x, which means du is equal to just 1/3 dx, and dv is equal to once again e to the 6x dx. So v is equal to 1/6 e to the 6x. So we cruise back over here, and we still have the 1/6 x squared e to the 6x, and we're going to subtract uv from that, which would be 1/18 x e to the 6x, and then we have plus the integral of v du. Why is it plus? Because it's minus in the formula, and that minus would turn the minus plus. So then we'd have once again 1/18 there, because of 3 and the 6, and e to the 6x dx. And I think we're about done here, so that'd be 1/6 x squared e to the 6x minus 1/18 x e to the 6x. And this is going to be plus, we're going to have to bring out another 1/6 to counteract that, so this is going to be 1 over, what is that, what's 6 times 18, that'd be 60, 108 e to the 6x plus c. Okay, so that's a nice integration by parts. At this point in the game, you guys should all be able to cruise through that one without much hiccups, so to speak. Okay, so here's number 5. This is a good example. We could use partial fractions here, or we could use trig substitution, or we could use arc sine, I think it is. Maybe I'll do it a couple ways. I'll start off with partial fractions. That's probably the way I would do it, because that's pretty straightforward. Because I would take over to the side here, I'd say this is equal to 1 over x minus 2 x plus 2, which would also be equal to a over x minus 2 plus b over x plus 2. And so then multiply everything by the common denominator, and I get 1 is equal to a times x plus 2 plus b times x minus 2. Now this is one where the cases probably make more sense. It's pretty easy if I let okay, stop that. How are you doing that? Let x equal -2. Then this disappears and I get 1 equals -4b, which gives me -1/4 is equal to b. And then if I let x equal 2, then this part disappears and I get 1 is equal to 4a, which means 1/4 is equal to a. So I got 1/4 of -4. So then I can rewrite this as the integral of 1/4 over x minus 2 minus 1/4 x over x plus 2 dx. And that's just a simple natural log. So that would be 1/4 ln of x minus 2 and minus 1/4 of ln of x plus 2. Isn't that sweet? Oh, plus c, that was a close one. Okay, so there's one that's can't use u substitution because x squared doesn't, the derivative of x squared is not dx. This is for trig substitution. Or you can't use partial fractions because you can't factor the bottom. So trig substitution though, this looks like a classic tan one. So because it's something squared, some number squared plus x squared. So if you think of 9 as 3 squared, so that tells me that I could write x as 3 tan theta. And if I do that, that means that dx has to be equal to 3 secant squared theta. D theta, of course. So then if I go back and recreate my integral, I'm going to have 3 secant squared theta d theta on top, because that's what dx is. And on the bottom, I'm going to have the square root of 9 plus 9 tan squared theta. Okay? So then, I'm just going to leave the top alone for a minute. On the bottom, I can factor out the 9, and I get the square root of 9 times 1 plus tangent squared theta. And of course, that's secant squared. So I got the integral of 3 secant squared theta d theta all over the square root of 9 secant squared theta. And now we get to cross some things out because we have 3 secant squared theta d theta over 3 secant. 3's cancel out, some secants cancel out, and we get the integral of secant theta d theta. So we're left with a, looks like fairly innocent integral, although secant theta is unfortunately not antiderivative of anything, so it's not a nice straightforward antiderivative, so we'll have to do a little maneuver here. This is going to be one of those moves where you say, how would I ever have thought of that? But like I say in class, there has to be a first time you think about it. So here it is. So in this case, I'm going to take secant theta over 1, and I'm going to multiply it by secant theta plus tangent theta. And I'm going to multiply the bottom by secant theta plus tangent theta. And of course, I'll still have the d theta sitting out there. I can do that because I'm just multiplying by 1. And I end up with secant squared theta plus secant theta tangent theta on top, and secant theta plus tangent theta on the bottom, d theta. Now, why on earth did I do that? Because now I notice that u is, if I make u secant theta plus tangent theta, then du is what's on top, because the derivative of secant theta is secant tan, and the derivative of tangent is secant squared. So then this becomes a du over u situation, which of course integrates to natural log of u, which is equal to the natural log of secant theta plus tangent theta. Now, of course, we can't leave it as theta. We've got to change it back to x's. So I'm going to draw my little triangle up here where it's in sight, and go back up and remind myself what the substitution was. Oh yeah, 3 tan theta. So that means that x over 3 is equal to tangent. So let's put a theta there. I get x over 3, which makes this thing the square root of 9 plus x squared, which is not a surprise. It's remember that always, we'd expect this thing over here to always show up in my triangle, right? And so now I'm going to go to work with this. So that would be the natural log of absolute value, and I'm going to replace secant with what it is. Well, cosine is adjacent over hypotenuse, so secant would be the other way around. Hypotenuse over adjacent, so that would be the square root of 9 plus x squared over 3. And tangent, of course, we already know it's just x over 3. So I just put x over 3 there. And throw a plus c in, and we are good to go. I'll give you that this little maneuver here is not a normal everyday move that I expect you to know, but I wanted to work past it so that I can get back to the subbing, because this is something, the triangle is something that I think a lot of you are still working on that you need to get better at. So there's an example of having to sub back in when you're done. Okay. Here's another, yeah, I think I'll pause because I'm going to pause the video here. Or actually, I'm going to end the video here, and I'll just make another one, continue to work on some more problems on this worksheet. All right.